this number is 1, right? And if solution does not exist, this number is negative 1. So this is the beginning, and instead of saying solution exists or not, we just write this, and then we calculate this value. And to calculate this value, we use basic idea. The key theoretical idea is using a to the power of half, right? P minus 1, right? These are congruent to mod P. Mod P. So we use this idea, but theoretically used, but practically, power calculation is not easy. Practically, it's difficult. Theoretically, it's very useful. This gives us the clue. So instead of relying on this, we develop certain properties such as these. When you have product of two numbers, a times b, then this is the same as a Legendre symbol a over p, Legendre symbol b over p. So we can split these composite numbers into these numbers. And when you decompose, we have two special cases, minus 1 or even number, right? Even number to some power, right? We have two special cases. But this is nothing but the repetition of this, so I will just focus on 2 over p. So these cases, and if we calculate this, this is the same as a to the power of p negative 1 to the power of p minus 1. Sorry, this isn't. Yeah, it's okay. Just this is okay, right? So if we interpret this, then when p is congruent to 1 mod 4, then it is 1. When p is congruent to 2 mod 4, then, p is congruent to negative 1 mod 4, then it is negative. So this, sometimes instead of the symbol, we interpret it, right? If p is 1 mod 4, then solution exists. If p is negative 1 mod 4 or 3 mod 4, then solution doesn't exist, right? So solution exists, solution does not, right? Solution does not exist here. So this is enough, but for practical purpose we do this. And in this case, we use this idea. So I covered up to this point, and if you have a question up to this point, ask me. And today we will cover the most important idea, called the reciprocity. So last time we covered all of these things, and finally we can break up the number, any number, right, into composite. Break any composite number into these numbers, and when you decompose, we make a negative number, we make an even number, right? So negative number is handled here, even numbers are handled here, and all the odd numbers can be handled in this form. Then this calculation will go on, but what if the number, or especially this position is big? Then we have very powerful theorem called the reciprocity, very important. Reciprocity. Then when you have p over q with odd prime, with distinct odd primes, then p over q can be written in terms of q over p with minus 1 to the power of this half multiplied by the other half. So as you can see, half number is extremely important, right? Half number is extremely important. So essentially, as you can see, minus 1, 2, or reciprocity, or has minus 1 to the power of something. There are three different types. So I will tell you the page number that you can find the proofs of these. And once you want to know how we prove this, you can find the place like this. I will write it. This portion is nothing but the rewriting of 1, right? This is nothing but from 1, right? A is negative 1. But this portion comes from page 177. And then this portion comes from page 181. And then this portion comes from page 186. So in case that I cannot cover all the details, you can go to these pages. So essentially by using these, we can calculate any Legendre symbol value, meaning we know that when we can solve problem like this mod p, right? When you can solve problem like this with mod p. So let's be more specific. This problem mod p, right? So when solution exists, when solution does not exist, is represented by just one symbol, simple symbol, and then we can calculate this symbol, meaning we can know whether solution exists or not by using these 5 properties. Of course, there are some trivial properties that you can consider, but please browse these 5 and ask questions. Essentially, in this chapter, our focus is covering these with appropriate amount of proofs. But as you can see, today is the essentially final day we can cover any new material, and the next time, like Wednesday and next Monday, I will review for the final, and then 1 week after that, meaning 2 weeks from today, the final exam. So please browse this and check whether you understand the meaning, not the proof. Once you understand the meaning, then it will be great. Then we can try to prove as much as possible. Yes? I try to do today or tomorrow. I will try to do today or tomorrow. Maybe today there are some other class and then some, so maybe tough. Maybe tomorrow I will try very hard to finish and post. And on Wednesday and Monday I want to use them to practice. Any questions? No questions on these? So, as I showed you before, for any 2 prime numbers, we can do the calculation, meaning we can know whether solution exists or not. So, up to this point we covered. And we may or may not be able to cover fully, but I will describe what theorems are involved to eventually prove this type of statement. What kind of things are necessary to prove this reciprocity? So instead of really proving, I will describe theorems because of lack of time, right? If you have like 1 month, I may cover all the details, but we don't have 1 month. So I will indicate what type of things are necessary. Instead of proving, I will describe the meaning. Page number 178, that is theorem 9.4 says this. Always P is odd prime, right? P is odd prime. Because when P is not odd prime, P is 2, right? P is 2. So it is too trivial to consider that case. So we always assume that P is odd prime. Then 1 over P plus 2 over P plus 3 over P all the way up to P minus 1 over P for the odd prime is some number. Some number is plus. All the possible choices are 1 or minus 1, right? 1 or minus 1. This is 1. This could be 1 or minus 1, 1 or minus 1. So we are adding 1 or minus 1 all the way up to P minus 1. Then, what is your guess? Will they be well balanced? And the answer is yes. They will be well balanced. There will be the same number of pluses and minuses if we add 1 through P minus 1. How do you prove it? You use the primitive root. Primitive root is the one having this property. This is achieved only when this is achieved only when the power is p minus 1. It's called the primitive root, right? This is the definition of the primitive root. P of p, right? This is achieved only when it is p of p. So with r, we can consider r to the power of 1, r to the power of 2, all the way up to r to the power of p minus 1. As you can see, these are not the same. These are incongruent. In other words, essentially these are the same as SS, these are the same as what? 1 through p minus 1. In other words, we are adding 1 over p, 2 over p up to p minus 1 over p. Right? Then essentially we are adding this over p, this over p, this over p, this over p. That means we are adding essentially so because of lack of time, I cannot mention the details, but some of you may get the idea immediately. So this is the state, this is the situation, right? 1 over p through p minus 1 over p is essentially this one reshuffled, right? This one reshuffled. So if we reshuffle it, we can get 1 through p minus 1. It's not in the order 1 through p minus 1, but in some order. Then, as you can see, power means we can multiply this outside, right? We can multiply this outside. Then, as you can see, r over p r over p is the same as r to the power of p minus, right, r to the power of half by the half property, right? This property, half property, right? By this half property, this is it, right? And can this be 1 or not? Can this be 1 or not? That's my question. Can this be 1 or not? Because it's a primitive root, this is achieved only when this power is what? P minus, so it cannot be achieved before. If it is achieved before, then it's not a primitive root by definition. So it is not 1 and it is negative 1. It means this is not quadratic residue, or this is quadratic non-residue. Because this quadratic non-residue is negative 1, right? So this is negative 1. Then from this point on, negative 1 plus negative 1 to the power of 2, negative 1 to the power of 3, negative 1 to the power of 4, all the way up to negative 1 to the power of p minus 1. Then as you can see, minus and then plus, minus and plus alternates, and eventually it becomes 0. So this is a proof. Even though I couldn't cover all the details, this is it. Any questions? So quadratic residues and quadratic non-residues are well balanced, right? Half is quadratic residue, half is quadratic residue. That's the reason why I mentioned half many times, right? The half is the key point in this consideration. Then there are some properties, and something that leads to very important property is Gauss lemma. It is page 179. Then half number is important, right? So half is 1, 2, and then the end is p minus 1. Then half is what? Half of this is p minus 1 over 2. This is the half, right? This is the half. So we focus on this half. We focus on this half. And then we multiply. We are considering whether a over p is 1 or negative 1, right? We are considering whether it's 1 or negative 1. So we are considering a over p is 1 or negative 1. We are considering half. So what? It is very strange. This kind of idea is the reason why math is so difficult. It's, for instance, when we solve differential equations, we know the direction. We know what to do. Out of nowhere, Gauss considered this strange set. Multiply a to each number here. So multiply a to each number to half, right? So he considered this set. And then what happens to this set? So out of nowhere, he considered this set. And then this gave us the breakthrough. So this is the non-trivial theorem, and this is the difficulty why math is so difficult. In some sense, it's like a jump in way of thinking, right? Jump. So people may think why people are considering this. This is Gauss, right? Gauss considered this. It's not usual people. Then he investigated. He checks whether it is less than half or greater than half, right? Less than half or greater than half. In other words, A multiplied by 1 could be less than half or greater than half. And then A over 2 could be less than half or greater than half. We don't know, right? After considering congruence, right? So after dividing these numbers by P, the remainder could be less than half or greater than half. So let's say this, we cannot specify it. Something is less than half. Then I will follow the text notation so that you can use later. Text to use R and S, and then text to use R for the remainder less than half. Right? Less than half. In other words, if you divide this by P, then the remainder is less than P over 2. Do you know what I mean? So less than half or greater than half. And then we divide something here. Then also, this might have the remainder less than half. In other words, it is all less than half. And then if we divide something here, I didn't specify because I cannot specify. Depends on A. If you divide some number here by P, then the remainder is less than half. And then let's say there are total, what did the text use? I will follow it so that you can later follow the textbook statement. So some number here is less than half. Some number here divided by P gives us the less than half remainder. And less than half remainders. And we collected all possible remainders having less than half. So I collected 1 through total M. Do you see it? Then the others have greater than half, right? So this may have greater than half. So let's call it S1. And then this has S2. And then this has S3, and so on. Then total could be S sub n, right? And this has greater than half remainder, right? Remainder is between 0 and P minus 1, right? Between 0 and P minus 1. The remainder could be less than half or greater than half. So up to this point is reasonable, right? Up to this point, but as I mentioned before, why did he consider this thing is mystery, right? This is almost impossible to think generally. But he considered this and then arrived at this. Arriving at this is not very difficult. Anybody can consider this thing in some sense, right? Because if you divide these numbers by P, the remainder could be less than half or greater than half. It's trivial, right? And then we just name the numbers having less than half like this, the numbers having greater than half like this, right? All generic. Then total numbers are how many numbers? 1 through P minus 1 over 2. So if we add this M and N, what is M plus N? If we add all numbers here, total M numbers and N numbers, then total how many numbers can you get? P minus 1 over 2, right? Because we are dividing this by P. We are dividing total P minus 1 over 2 numbers by P, and we sometimes have less than half and greater than half. So total number M plus N is P minus this one. Then he wanted to squeeze these numbers to smaller space. Currently, the remainders are spread all over. The remainders are less than half and greater than half, meaning the remainders are spread between 0 and P minus 1, right? So this is the idea. Gauss idea is amazing. The remainders, so there are total P minus 1 numbers, and the remainders are spread all over, right? All over less than half or greater than half, right? This is the middle point. But it didn't fill all the positions, right? It didn't fill all the P minus 1 positions. Only we have P minus 1 over 2 numbers. So what he considered was squeezing this back into this portion instead of this. How can he do it? He considered say this is Si, then P minus Si. What happens to P minus Si? Si is greater than half, then P minus greater than half is what? Less than half. So he tried to locate these in this position, like this, right? And then he tried to locate them in this position, and then checks whether there is a match. In other words, some number may have the same number like this, right? So will it happen? And he proved that this doesn't happen. In other words, if we squeeze them, it will be a perfect match. If you squeeze them, this kind of thing doesn't happen, right? In other words, if you consider P minus S sub I, then it will squeeze this all back inside this smaller, in other words, half space. So it's a perfect match. So this is the key to the reciprocity, right? Quadratic reciprocity law, which is extremely important. So please browse the idea part and check. I will pause, and you may browse your note to check it. In other words, he considered the half set, right? Half set, not just half set, A multiplied by half set, right? And then divide this by P, then the remainders are sometimes less than greater than, it's spread all over 0 through P minus 1. But he tried to squeeze them in to just the less than half portion. Then what he did was very simple. Oh, now it's very simple. Let's multiply all these numbers. Let's multiply all of these numbers. Then it's like this. Oh, this number is the number between, right? Between 1 through P minus 1 over 2, right? Because we excluded the 0. So 1 through P minus 1 over 2, right? 1 through, because we excluded 0. Well, the usual remainder could be 0, but we removed the 0 in the first place. There is no 0. So we have these numbers in between, right? So we are multiplying these as S, not specific entries, but as S. Then multiplying these is equivalent, right? Multiplying this is equivalent to multiplying Ri and then P minus Sj, right? I and J could be used as I used J. In other words, multiplying all these things, right? This is his idea. So do you get it? Well, if you don't, ask me. I will pause in this part. Even though I hurry up, because this is the key part, I will pause. So take a look. This is the idea. He multiplied the half set by A. And then he checked whether the remainder is less than half or greater than half, and then split. And then the greater than half remainders are squeezed back using P minus Si. And then he showed that they cannot be equal. In other words, there is no straightforward match between P minus Si and Ri. There is no match. In other words, they slide in to these empty positions perfectly. Amazing. This kind of thing is amazing discovery, right? He discovered. Then, because it slides in perfectly, and there are total P minus 1 numbers, multiplying 1 through P minus 1 is the same as multiplying all the remainders like this in this form. Do you get it? Almost done. Then, just simple routine technique will finish it. So let's do it. If we do it, then 1 multiplied by 2 multiplied by 3 multiplied all the way up to P minus 1 half, right? Is congruent to R1 multiplied by R2 multiplied by Rm multiplied by P minus S1 multiplied by P minus S2 multiplied by all the way up to P minus Sn, right? I used R and N. Then as you can see, we can remove P with mod P, right? With mod P, we can remove P. P is the same as 0. Then it is the same as minus 1 to the power of what? How many numbers have minuses here? Total n, right? N numbers have minuses. Then with this, it is nothing but R1, R2, Rm, and then S1, S2, Sn. So this is the idea. So please browse this and ask questions. Now we return back to the original. In the first place, R and S are nothing but the remain. Yes?
The notation is negative 1 to the n?
Right, n.
It came to the s, right?
That's right. So we return back to the original form. R's are nothing but, R and S are nothing but remainder when you divide some number by P. In the first place, how did you get R and S? Go to the first part of the proof. How did we get R and S? Right? We considered 1 multiplied by A, right? A multiplied by 1, and then A multiplied by 2, and then A multiplied by 3, all the way up to A multiplied by half. So we multiply these numbers by A, and then divide this by P. Then the remainders are R1 through this. And then these are, with mod P the same, right? Mod P, these are the same as SS, not individual component-wise, but SS, these are the same. So I wrote these things up to this point and please check whether you completely follow me or not. And then, as you can see, 1 through P minus 1 over 2 are relatively prime to P. So we can call this L, and then we can call the multiplication of these things L. Then GCD of ln P is equal to 1 because they are relatively prime. Because of this reason, we can cancel out, apply the cancellation law. Then the left side is 1, the right side is minus 1 to the power of n, and then a to the power of half with mod P over GCD, right? P over GCD, but GCD is nothing but 1, right? By the cancellation law. Important technique, right? Cancellation law. So essentially, if we multiply both sides by negative 1 to the power of n, what happens? If we multiply both sides by negative 1 to the power of n multiplied, and then right side negative 1 to the power of n, and then negative 1 to the power of n, a to the power of this, and then mod P over G, G is 1, so mod P. Then as you can see, negative 1 multiply power of n multiplied twice is positive no matter what. So we can remove this. Then by principle 1, right, half principle, what is the right side? By the principle 1 that I summarized, what is it? A over P, right? Look at the principle 1. That I gave you 5 principles. Principle 1. So as you can see, quadratic reciprocity A over B is nothing but negative 1 to the power of n, which exceeded half, right? Which exceeded half, meaning the remainder exceeded half, right? Remainder exceeded half, right? Which remainder exceeded half is collected, right? Total n number. This is it. So this is the breakthrough discovery leading to amazing theorem called quadratic reciprocity. And I completely settled the matter, even if I couldn't cover all the details. But I think you get the picture. But as you can see, it's not easy. For instance, someone gives you time and all the resources and goes to the mountain and then prove it for 20 years, may not prove this. So unless you stop me, I will go to the next page. If you want to stop me and ask questions. So how can you calculate A over P, I mean redundant symbol A over P? Just count the number which remainder exceed half, right? That's it. And then minus 1 to the power of that number. Then, why is it so important? Because the next portion will show you. So, the idea, the small lemma is this. Now A over P is suddenly, I take a look, I'm summarizing it. A over P is theoretically calculated by half power, right? A to the power of half. But that is essentially the same as minus 1 to the power of n, which exceed, right? Which is the number of numbers, number of integers exceeding, which remainder exceeding the half, right? And then this is suddenly is congruent to minus 1 to the power of this number. Adding all the numbers, I don't want to use summation formula. I will use just simple, straightforward idea. A times 1 over P with floor, and then A times 2 with floor, and then all the way up to A times half. Half is P minus 1 over 2, right? Floor. So n can be now theoretically calculated. N can be theoretically calculated. So half is extremely important in this, right? Half, all the time half. So this portion is small lemma, and the proof of this lemma is on page 183. And if we have enough time, I will return back to the proof of this part. If you don't, then unfortunately we cannot cover this proof in this course. With this one, now we arrive at the reciprocity, quadratic reciprocity. So eventually we will arrive at this. I will write it and say it. The reciprocity law. Using this we can prove. So take a look. How far should we come to prove this? We need the definition and this brilliant idea, Euler's idea, and then not just Euler's idea, unbelievable idea by Gauss, right? And then some small lemma. And then from this small lemma, reciprocity. Boom, this is the end of the story, essentially. So I will pause so that you can browse the idea and then understand the importance of this and the proof. And then afterwards, I will return back to this relation. So I will pause, and then you can check whether you follow the idea of this sketch-up proof. Then let's do it. So with this, we want to finish it. So I will multiply both sides by Q over P. I will multiply both sides by Q over P. Then I will get the equivalent statement, right? This is the equivalent statement. But what about Q over P multiplied by Q over P? The Legendre symbol Q over P multiplied by Q over P is what? So it is equal to what? Right, 1. Cube, something squared is 1, right? So because of this, it's squared, and then squared gives us 1, right? And then this. So essentially, I will prove the equivalent version to the previous one. So what I will prove is this one on even text has this form. Practically, we use the above form, but it looks neater, right? It is very it looks very symmetric, so we can prove this portion. So finally, how can you prove it? this is the idea. Also, half is extremely important. So I will follow the older text used. Text used P in this direction. So this is P, this is 0, this is Q. Right? This is P, this is 0, this is Q. And now P minus 1 is a little bit less, right? P minus 1 is a little bit less. P minus 1 is a little bit less. And then half, right? Half of P minus 1 is about here. Do you see it? Right? P is here, P minus 1 is here, and half of this is right here. Same way, Q minus 1 is here, half of Q minus 1 over 2 is here. In other words, this position is right here. Right? So please browse this and ask whether you understand it or not. Then we want to connect 2 points. This is 0, 0 point and a PQ point, right? 0, 0 and PQ points are connected by a straight line. So I connected them. So if you have a question, ask me. I connected 0 and 0, 0 and PQ point, right? 0, 0 and PQ point. Then, what does the lemma say? Lemma says this. Oh, if we want to calculate something like Q over P, then we need to count minus 1 to the power of what? Q times 1 over P, right, times, and then Q times 2 over P, and then Q times P minus 1 over P over 2 over P, right? Over 2 over P. By the lemma that I mentioned, right? I will go up and show you the lemma, right? By this lemma, right? By this lemma. When you have A is replaced by Q. Do you see it or not? Do you see it or not? Then take a look. These are nothing but this line. This line is given by QP, right? So this line is like this. Y equals Q over PX, right? Do you see it? Y equals Q over PX, this line. Then we follow this line and count the number satisfying this. We are counting. Now counting area will be marked. So counting area is here, right? From, it's not exactly 0, 0 somewhere, right? So I will just point this kind of picture, right? So even though it hits some line, it doesn't mean reality. So we are counting the integer grid point in this rectangle. It went up, but this is a bad sketch, but it doesn't go up. This line is above, right? So we are counting the integer. Then we are counting the integer point under this line. Then somewhere, like you assume that this is 1, then this is somewhere, right? And then somewhere here, somewhere here. It doesn't hit the line, right? You cannot hit the line. So take a look. It's like this, right? So we are counting all the integer points like this. Do you see it? So this sum is nothing but the integer points between these. So if you don't understand, you can ask, then I can very, very slowly give you the idea. In other words, this is possible integer point in this, and this is possible integer point with x equal to 2, right? Take a look. Q over P is everywhere. Q over P is everywhere. So x is equal to 1, right? X equals 1. X equals 2, x equals 3, x equals 4, x equals 5, and so on. then each time we get integer points, right? So all the integer points are collected here, right? So I will use visual effect. Visual effect is all the integer point in this portion, right? In this portion. All the integer portion in this portion is here. And the same way, by the same reasoning, we can get this idea. P over Q is minus 1 to the power of, we reverse P and Q, right? We reverse P and Q, Q times 1, P. Then we consider the graph using rotation. Then we are counting the integer point like this, right? We are counting the integer point like this, right? It is not clear, but it's better to use different colors, right? So we are counting all the integer points, right? All the integer points, right? So in visual effect, this sum is essentially all the integer points counted in this form, right? So this is it. So we are calculating P over Q using the lemma, right? By the lemma. We are calculating P over Q by the lemma. So by using lemma twice, we get these. And then we visualize it. Then all the inner grid point inside this triangle, all the grid point inside this triangle are the points. Then now we are multiplying. I will go to the, yes?
So then, should that be P times 1 over Q for the first floor?
P times,
Because we switched.
thank you, you're right. Why did I do that? P and then Q. Thank you very much for the correction. So we are now using the lemma. Lemma says this, and then we analyze. This analysis is very exciting and not very difficult. If you have enough time, instead of using PQ, use two prime numbers, such as, for instance, 11 and 13 or something you like, right? And you can see the effect. And in fact, I will show you later. But in any case, we are multiplying these two. We are multiplying these two numbers, then we are multiplying the right side. So multiplication here becomes multiplication here, and the multiplication here has become exponent-wise what? If you multiply two numbers, exponent-wise what? Addition, right? In other words, multiplication of the left side means addition of these up to half, right? And then the other half, right? Addition of the other half. And then addition of the other half is nothing but addition of the integer point here plus addition of integer point here, right? Addition of integer point here and addition of integer point here. Then we are adding all the possible integer points in this rectangle. Suddenly, we are having very trivial shape. Up to this shape, it's very difficult to really count the number exceeding half, count the number of integers below the line. But suddenly we are having a very simple shape, rectangle. Inside the rectangle, how many integer points can you find? Integer grid can you find inside this rectangle? So take a look. This is 1, 1. This is this. Then total, how many integer grid points can you count? Can you find? Right? This direction has 1 through p minus 1. This direction is 1 through q minus 1 over 2. So total, how many points? Total p minus 1, q minus 1 points, right? So suddenly out of nowhere, very simple shape is created, right? Only thing that we want to consider is just the integer points between 1, 1 and this. Then if you count the number of grid, it's not very difficult, right? To correctly solve this problem, which grader is required? First grader, second grader, third grader. Which grader can handle this properly? So you give a problem. Oh, I will write it, and then I will write the point, and then this is 2, and this is 9, right? And then this is 2, and then this is 1, and then this is 7. Then how many integer points can you count? 2 through 9 means total 8 points, right? Total 8 points in this direction. 1 through 7 means total 7 points. Do you see? So total 56 points, right? Which grader is required? Maybe 6, 5th. You can count the number of integer points, right? Suddenly, Gauss made that problem into this simple problem, right? So this is the end of the story. So I sketched the proof. Now it's time for you to browse the whole idea leading to the reciprocity law, and then check whether you completely follow it or not. And if you have difficulties, I will answer. But if you don't, then I will return back and then cover a few cases that I couldn't show you, or some new result that I didn't even mention. So please browse and ask questions. Your note and check whether you completely follow it or not. As you saw, triangle is tough to handle, right? When you have triangle, counting the number below it is tough. So let's use an example. For instance, you may pick 2 primes to practice this essential part, because with this we could prove it. So it's a good idea to examine it. So please pick 2 primes. What primes do you like? Maybe 5 and 7, right? 5 and 7. So 7 in this direction, and then 5 in this direction. Then half this number is 6, and then 6 over 2 is 3. Do you see it? And then 4 is this, and then half of this number is 2, right? 3 and 2. Do you see it? So this is it, right? Then from 1, 1, essentially we started with 0, 0, right? We started with 0, 0 is not counted, so from 1, 1. So in fact 1, 1 is around here, 1, 1. And then from 2, 3, how many points are there? 1, 1, 2, 1, 3, 1, right? 1, 2, 2, 2, 3, 2. Total 6 numbers, right? In this case, total 6 numbers. Do you see? So I will prove it. So all we need to consider is this number. For instance, 5 over 7, right? 5 over 7, right? 5 over 7 multiplied by 1. And then 5 over 7 multiplied by 2. And then 5 over 7 multiplied by 3, which is the half, right? 3 is the half. Do you see it? So this is the one above the power, right? Above the power position. Then from this, what do you get? 5 times 1 over 7, we get 0, right? Floor of this is 0. And then 10 over 7, 1. 15 over 7 is 2. So the total 3 numbers we could count, right? So below this, we got 3. Then what about the other direction? 7 over 5 multiplied by 1, right? And then half, right? 7 over 2. 2 is the half with 5, right? Do you see? With half, 2 is half of 5, right? 5 minus 1 over 2 is 2. So this is it. Then from this we get 1. From this we get 2. So total 3. So how many numbers did we get? We get 3 here. 3 are total 6. As you can see, if we use triangle, we need to do these calculations. For specific numbers, it's not very tough. But for general number, it's not easy. It's not that easy, right? So this is the toughness in general. So this is, if I really count it, for 1, there is nothing. In other words, if I correctly connect, it's like this. I used the curve to miss something intentional. Yes?
Is this more p times q?
Excuse me?
Is it more p times q?
P times Q? I don't understand. It is PQ is this position. PQ is this position. This is half position. So if we connect this, then the line does not hit this point or hit this point. Line is in between. So can you rephrase your question? What was?
I don't. Is it more p times q? Is p over q times q over p is more p times q?
I don't understand the question. Can anyone? So let's discuss this later. Is that okay? Then let's check it. Take a look. If we follow this, then on this line, one line, we get 0 under the triangle, right? Under the hypotenuse of triangle. And then if we count this position, then it is 1. And then if we count this, then 2 points, right? So total 3 points. Do you see it? Now, if we count this, then we find 1, right? That means if we count in this direction, then we find 1, right? And then if we count above this, following this 2 line, then we get 2 points, right? So that's the reason why we get 2 here. We get 2 here. So essentially, this is the reason why we get the simple shaped rectangle. This is all the positions in between, right? P over Q is not an integer, right? Only when you use P or Q on the other side, it hits the point. But other than that, it's impossible to hit. So I explained all the necessary part of the proof and even showed you an example. And you can examine this portion in detail. Then, before proving something that I left behind, I will explain a few other cases that I couldn't explain. First of all, corollary that I did not mention was this. All the quadratic residues are, so quadratic residues are nothing but some primitive root to the odd even power, right? So R is primitive root, right? Primitive root. So R is a primitive root. Then all the quadratic residues are R to the power of even power. And all the quadratic non-residues are R to the odd power. Right? It's obvious. I showed you that if you add all these things, then minus 1 to the power of 1, minus 1 to the power of 2, up to minus 1 to the power of p minus 1. So this is the corollary that I couldn't even mention. The next idea is 2 over p using this idea, right? Using the idea, using Euler's, right? Euler's, Gauss did, right? Gauss amazing idea, right? Gauss idea lead to this p over q is 1 or negative 1 when, this can be written in this form. This can be written in this form, minus 1 to the power of p minus 1 over 8, right? P squared minus 1 over 8. So this is from Gauss idea. Rewriting the Gauss idea is this. Unfortunately, I didn't have enough time to show you all the details. And the next thing is this. When we have 8k plus 7 or 8k minus 1, right? 8k because k is used here, I will use 8l minus 1. The same form, right? How many primes of this pattern can you find? How many primes of this pattern can you find? And the answer is infinitely many, right? There are infinitely many primes of this form. And we can prove this fact using the Gauss idea. Unfortunately, we didn't have enough time. We don't have enough time to even mention. And other portions are the reciprocity law we explained. So take a look. It is reciprocity law we explained, and people spend time on this fact. Can we really tackle the problem using the reciprocity? And the answer is yes. We can tackle this problem using reciprocity. So I will describe the result. Page number. Page number is 189. And this is theorem 9.10. We don't have time, but we can handle this reciprocity. Sometimes it's 1, sometimes it's negative 1, and this can be handled by reciprocity. Unfortunately, we didn't have enough time to cover. So roughly, these are the cases we can consider. And because we have about 15 minutes, you may ask any specific thing to prove, then I will prove. Or you may ask me to show you examples of using reciprocity, then I will show you examples. So either way is possible, because only 15 minutes, I will follow your decision. Great. So assume that you are asked to handle this kind of problem using reciprocity. Then 3 over p, you may pick any p. You may pick any p, then I will follow you. Did you say 7 or 17? Yes. 7. Then, by reciprocity, this is the same as 7 over 3 with minus 1 to the power of what? Half-half, right? Half-half. Do you see? Half-half. So, 3 minus 1 over 2, 7 minus 1 over 2, right? Then this is 1, and this is 6 over 2, 3. So it's negative 1, right? So it is negative 1 after doing it. Then 7 and 3, congruence. You can use congruence. With 3 hour clock, 7 o'clock is the same as what o'clock? 1 o'clock, right? And 1 has always solution, right? 1 is 1 squared, right? 1 has always solution. So this is 1. This is negative 1. So negative 1. In other words, if we translate this back to the original, x squared is 3 mod 7 doesn't have a solution. it doesn't have a solution. So check it. 0, of course, we should exclude 0, right? Trivial. 1, no, 1 squared cannot be 3. 2 squared is 4, not 3. 3 squared is 9. 9 is congruent to 2, right? 4 squared, 16. 16 is congruent to 2, right? And then 5, 25. 25 is congruent to 4 minus 7. 21, subtract. And then 6 squared is 36. 36 is congruent to 1. So we couldn't find anything satisfying. But did I really do the hand calculation? Can you do the hand calculation when I use 4-digit numbers here and 3-digit number here? If you do the hand calculation, it will take forever, right? Even if you have like 1 month, you may not be able to get the correct solution with 3-digit here, 4-digit here. So let's do the challenging job. You pick any 3-digit number and 4-digit number, then I will do it. So you pick. Then I will find the closest prime number to your choice. So pick P, which is a 4-digit number, and then A, which is a
4,909.
and then
909.
so these are the numbers that you pick. Then I will pick the closest number to this and then solve that kind of case. It's not a setup. I completely calculate this by principles, not by
909. 4909.
I say 4909. Then so 4909 is the prime. How did you know that? And then 409 is, did you pick this number or? Primes up to 909, then the last prime number 907. So you chose this problem. Question is 907 over 4909. This is the question, and these are primes. With this form, you may say 1 over minus 1, then the best point that you can get out of 20 points is like 1, even if it is correct. But you need to explain why this is so. So I will use reciprocity. Then 4909, 907, and then minus 1 to the power of half, minus power of half, right? So we are multiplying half. And as you can see, if you subtract 1, this 8. 8 divided by the 2 is even. Once it's even power is even. So this is 1. Gone. If you don't understand, ask me. I will solve all the details. I will show you all the details. Then now, all you need to do is 4909 divided by 907, then about 5 is okay, right? 5 is. Then subtraction gives us 4, 7, and then 3, right? 3, 7, 4. Please check and ask questions. But I want to reduce further. Oh, that's okay. This is good enough right now, and later I will do it. 3, 7, 4. So by congruence, this is equal to 3, 7, 4. Suddenly, take a look. We are not handling 4-digit number anymore. You began with 4-digit number, right? Size of a 4-digit number. But by just one step, it is 3-digit number over 3-digit number. But if you go one more step, it will go down significantly. So this is the power of reciprocity. Why do we need reciprocity? If you want to design very sophisticated, state-of-the-art circuits, you need these steps. Not all the time, but in many cases. Then take a look. We break up. 3, 7, 4 divided by 2 gives us what? 3, 7, 4 divided by 2 gives us 1, and then about 8, and then 7, right? 187 divided by 11 gives us what? Oh, it is like 1 and then 7, right? So we broke this up. We can break this up into 3 numbers. 2, 11, and then finally 17. So please check it and ask questions. I just broke up the top part, right? It's not numerator, it's Legendre symbol, but it's still in the position of numerator. So I broke up with the same denominator stuff. So it doesn't make any sense if you use fractions. Fractions do not satisfy. Legendre symbol satisfies. Then 2 calculation. 2 calculation requires what? Minus 1 to the power of what? P squared minus 1, right? P happened to be 907, but if you divide by 8, what do you get? If you divide this by 8, then 1, then 8, then 1, 0, and then 1, then 8, then we get 27, then 8, if you divide this by 8, then 3, right? 24, and then 3. So do you see it? So 113 is congruent to 3 mod 8 because we are dividing by 8, right? So 3 squared minus 1 over 8 is congruent to 113 squared minus 1 over 8. They are congruent, right? Because 8 is cancelled out, right? 8 is cancelled out by this. So with this, it is what? 9 minus 1 over 8. Then 8 over 8, it is 1, right? So it is negative 1 to the power of 1 and negative 1. So I calculate the first part. Then the second part, 11. As you can see, I don't want to handle big, like a lower position number, right? So I will say, 907 upstairs and then 11 downstairs. Then what should we attach? Minus 1 to the power of what? Half, right? Half and then half. Do you see it? Reciprocity. And then I will do the same thing to 17 part. I will reverse reciprocity. I will use reciprocity and the minus 1 to the power of 907 minus 1 and then 17 minus 1. So these are all trivial. Why? Because 907 minus 1 is 906. 906 divided by 2 is odd. Check odd or even, right? It's odd. Odd, and then 10 over 2 is also odd. Odd multiplied by odd is odd. Power is odd. So from this, we get negative 1. Do you see? From this, we get negative 1. And 16 over 2 is 8. Even, then it's 1, right? Done. So all the signs are handled. Now, by congruence, we can simplify. By congruence, we can simplify it. 907 mod 11, right? 907 mod 11, then about 8 will be enough. 88, then it is 27. Then 2 is enough, 22. Then 5, right? So I can write it this way, 5, 11, right? 5 over 11 is not fraction over, it's Legendre symbol over. And the same way, we can simplify. 907 divided by 17. So 907 divided by 17 gives us 5, 6 is too much, right? 5 is good enough. and then 5, 7, then about 3 is good enough, right? 3, 51, then 6. Do you see? So it is 6 mod over 17. So take a look. Minus multiplied by minus is plus. So all we have now is 5 over 11, 6 over 17. Then we can repeat it. 6 over 17 can be broken up into 2 parts. 2 times 3. Do you see? And then this can be what? Reversed. So I'm using it over and over again. Then it is 11 over 5, and then minus 1 to the power of half, right? Half. And then 6, this can be broken up. Right? So I broke up these numbers. And then, as you can see, this is 4. 4 over 2 is already even. Once you see the even, this is gone, right? 1, right? Because it's even. Then 11 over 5 is 11 divided by 5 gives us the remainder 1. Gives us the remainder 1. Do you see? 11 over 5, the remainder is 1. This is by p squared minus 1, right? 8, right? 8. And then this is what? 3 over 17. We use reciprocity. 17 over 3. And then minus 1 to the power of half, right? Half, half. If you don't understand, ask me. P, which is congruent to 17 mod 8, right? Then, as you can see, 17 is congruent to 1 mod 8. So it is 1 squared, so this is gone. And then this is 16, even gone. And then 17 over 3, this is 1, this is 1. This is 17 over 3 is 2 over 3. And then this is 1, right? Then, as you can see, 2 over 3 is negative 1. No solution. What you chose has no solution. In other words, this could be the final summary. X squared is congruent to 907 mod 4909 has no solution. Why? Because of this. So number means something. Number means something. So this is the end of the story, and next time I will try to make the sample problem test and solve the problems with you, and you may ask questions. You have 2 weeks to prepare for the final exam, and if you didn't get nice score on exam 1 or 2, solve as many homework problems as possible by the final exam day, and then you turn those things to me. Then if your score is above the point that I mentioned, then your final can completely replace all the bad scores that you might get. So let's stop now.